So this is assignment 3 on thermal stress, and we're going to take a look at problem 1. Calculate the heat stress associated with the following environments. Commercial laundry, natural wet bulb is 34 degrees centigrade, and the globe temperature is 29 degrees. Okay, so we have a formula for that. We're going to use the indoor formula, WBGTN, and we have the natural wet bulb, and we have a globe temperature as part of that formula. So I'm going to pull up a piece of paper and get a little bit more room there. Oops. And let's give this a try. Let's see. Okay, so WBGTN is going to be equal to 0.7 times our natural wet bulb temperature, 34, plus 0.3 times 29 degrees centigrade. Okay, let's get our calculator up and do this calculation. Okay. Let me clear out my memory. 0.7 times 34 is 23.8. I'm going to put that into memory and clear this. And 0.3 times 29 is equal to 8.7. And I am going to, oops, let me get that 8.7 back. And I am going to add the quantity that's in memory to that, and we get 32.5. WGBT effective is 32.5 degrees centigrade. Okay, so that would be our answer for that. If we move on to the next one, which is very similar, I'm going to clear this out and ask about a foundry worker in this time. And this time we're going to be looking at, okay, let's see. This time we're going to be looking at 0.7 times 28 degrees centigrade plus 0.3 times 44 degrees centigrade. So we're cooler in that environment, but there's a lot of radiant heat probably off the furnace or whatever operation that he's working on there, since it's a foundry. Okay, 0.7. Let me clear out memory to write that, times 28. Let's put that into memory. And 0.3 times 44. And let's add our quantity of memory. And we have 32.8. So we had 32.5 and we had 32.8. So given what we have been told here, activity is more likely to cause heat stress. Well, given that we haven't been told any other information about metabolic rate or anything like that, I would probably pick foundry here, just simply based on the wet bulb globe temperature, the effective wet globe temperature in the two environments. You know, I hate to say this, but perhaps you could consider putting not enough information, because we don't know the metabolic rate of the two workers. We don't know activity level that a commercial laundry would be working at versus a foundry. We don't know. Maybe the foundry is just looking at an operation, not very active. Maybe the laundry, he's folding laundry and he's quite active. So without knowing that, assuming that they have same metabolic rate, probably foundry is the best answer. If we don't want to make any assumptions at all, well, gee, we would really need some more information. So I think I'm going to go back to that and accept any answer that you put down there. But consider that. If we, you might consider not enough information, just based on the fact that we really don't know much about the level of activity that the work involves. Okay, I'm gonna set this up so I can get to the next one. Okay, calculate the wet bulb globe temperature, time-weighted average, when workers exposed to the following temperatures throughout the day. For 2 hours at 78 degrees, 10 hours, 2 hours at 80, 2 hours at 84, 2 hours at 87. So basically, it's going to be pretty simple. We're just going to calculate the time-weighted average over the total 8 hours that he was working. So that's going to be equal to let's see, 2 times 78 plus 2 hours at 80 plus 2 hours at 84 plus 2 hours at 87 degrees. All of that over the total number of hours worked, which is going to be 8 hours. Okay, if we just grab our calculator. Okay, let's see what we wind up with here. Okay, clear out memory. Okay, 2 times 78. Let's put that into memory. Okay, 2 times 80. And we're going to add that to memory. 2 times 84. And we're going to add that to memory. And 2 times 87. Okay, 174. We're going to add that to memory. I'll clear this. I'll recall memory. And I'm going to divide by the 8 hours. Equals 82.25. Okay, 82. Whoops. Pen. 82.25. Okay, I could round it, I guess, to 83. Let me just go back to our, clear that, go back to pointer, so I can get back to our page. Okay, and next we have the question, which is using the information provided above, assume the worker is wearing a polyolefin coveralls, is performing moderate work. Is he or she above the threshold limit value or action level? Let's take a look at that. We have that in our PowerPoint presentation. Our metabolic rate, we said moderate work. So for moderate work, metabolic rate is 300. And let's see what we have here. Well, first we're going to have to do a conversion. We are going to have to convert our 82.25 degrees, I believe it was. I erased it now. 82.25 degrees. We're going to have to convert that into Celsius. So Fahrenheit, oops, to Celsius. See if we can get a 82.25. Okay, is equal to 20, basically 27.9 degrees Celsius. Whoops. Whoops. A little clumsy here with this new version. Let me get this kind of compact again. Okay, so 27.9 is what we wound up with. And I think there's an addition for the coveralls. So if we can find that quickly. Here we go. Clothing adjustment factors, polyolefin coveralls. We're going to add 1 degree C for the coveralls that he's wearing, because they're non-breathable. Okay, and so we're at 27.9 plus 1, 28.9. Let's go back to our table. 28.9. So we have a metabolic rate of 300, and we have, let me highlight this. We have a metabolic rate of 300. Whoops, not quite straight. And we have a WGBT effective of 28.9. So it would appear, actually we would be over here, and this would be about over here. So it would be, appears that we're above the TLV. So we would say in answer to that question that we are above the action level and TLV. Okay, a little hard to see because I didn't draw that straight line right on the 300 there, but you can kind of see that we're up there pretty high. Okay, and let's see, above the TLV. Okay, and you notice that we might have been right at it if we forgot to take account for the fact that we said he was wearing those coveralls and correcting those coveralls. Okay, so a little bit of a trick question there, I guess, but you got to remember to include those. Okay, work rest cycle. So now, see if we can't find out work rest cycles. Okay, and here is our chart for our work rest cycle. So I'm going to go to acclimatized work. Doesn't say anything about it being an unacclimatized worker, a new worker. So I'm going to go right into our acclimatized workers. And let's see. Okay, metabolic rate 300. Actually, I'm not sure which one we are looking at here. I'm thinking it's this one. It would be moderate. Okay, let's take that one as moderate. And if I assume that the metabolic rate that was on that previous chart, which I guess wasn't, I'm thinking that it wasn't, the units were not there. Let me see if I can't get back to it. I need a pointer. Let me get back to that and see if the units were present. Metabolic rate in watts. Okay. Okay, so here's a metabolic rate in watts. Okay, we said 300, so we're over here somewhere. Okay, let me see if I can't kind of get semi-straight line here. Okay, I'm going to say 300. It looks like it's going to be around here somewhere. And I'm going to go up as straight as I can here. And let's see, environmental heat. Okay, let's move this down. WGBT of 29. Actually, we have both of them Celsius scale next to it. 29. 29 would be about here. Okay, so I'm going to go across from here. And it looks like we can tolerate, let's see, 45 minutes of work with about a 15-minute rest cycle. Okay, hopefully this chart that, it's a little bit of a twist here because you got to go back and make sure you're looking at the right units here. And so this isn't a very forgiving chart that way. And it's a little hard to see as well anyway. And there isn't much leeway. These lines are pretty close together. So I would, in this case, say that we'd be a cycle of 45 minutes, recommended cycle would be 45 minutes of work with 15 minutes of rest. If I get talked into it, I could probably go back and just turn off the checks in my, if you wound up with 30 minutes, I guess you could, I don't think, no rest required. I don't think that's reasonable. And I think you have enough information. So I think either one of these first two, if you hock me enough, I'll go back and make it so that it'll accept any answer. So you get the grade right anyway. Okay, so that's what that one looks like. Let's go on to the next problem. Okay, 54-year-old worker has a sustained heart rate of 135 beats per minute. Is this work rate too high for the worker? Okay, so this question asks, question number 7 asks, a 54-year-old worker has a sustained heart rate of 135 beats per minute. Is this work rate too high for the worker? Okay, let's take a look at our rules for guidelines for limiting heat stress where heart rate is concerned. So sustained heart rate of 180 beats per minute minus the individual's age would be appropriate for normal cardiac performance, people that are normal, healthy. Okay, we also have core body temperatures that we discussed, and recovery heart rate after 1 minute of rest, the heart rate should not exceed 120 beats per minute. Okay, so in other words, if you have elevated heart rate and you're at rest, you should, after 1 minute, recover so that your heart rate is under 120 beats per minute if you're not being exposed to excessive heat stress. So for in our case here, 135 beats per minute, so we have 180 minus the age of the worker, who's 54. So 180 minus 54 is certainly less, it certainly is 126, which is certainly his heart rate of 135 is more than the maximum heart rate that he should be sustaining over a period of time. So the answer to this, is this work rate too high for a worker? The answer would be yes to that. Okay, question number 8. What is the air velocity in feet per minute required to provide 1,000 BTUs of evaporative cooling if there's 35 millimeters mercury of water pressure, vapor pressure of water in the air? And let's see if we can't find that. Okay, and I know we have it here. Evaporative rate, convection, radiant, and evaporative heat loss. So here's our formula for evaporative heat loss. E is equal to 2.4 times the velocity to the 0.6 power times the difference of the vapor pressure of water versus subtracted from 42 millimeters of mercury. So let's see if we can't work this out. So the evaporation rate is 1,000 BTUs per hour. I'll leave the units off for now. Is equal to 2.4 to the and times the velocity to the 0.6 power times the 42 minus 35 millimeters of mercury. Okay, so that's 7. Okay, we're going to divide both sides by 7, and well, actually, we can multiply both sides by 7 times 2.4. 2.4 times 7. So V to the 0.6 power is equal to 1,000 divided by 2.4 times 7. Okay, let me get the calculator out. Oops. .4 times 7 equals 16.8. I'm going to put that into memory. And 1,000 divided by, the result of that is 59.52. 59.52. Okay, so now we have to solve for a v in order to complete this.
This conference will now be recorded. This conference will now be recorded.
Okay, so let's continue with this analysis and let's see what we wind up with here. At this point now I can say I'm going to take the log of both sides because the log of v to 0.6 is the same thing as 0.6 times the log of v. I can take the log of both sides. I'll take the log of this side, which gives me 0.6 times log of v. Okay, the log of excuse me, if I have b to the a power and I take the logarithm of it, you would have the log a times the logarithm of b. Okay, that's how we would find the logarithm of that number. So 0.6 times the logarithm of v is equal to the logarithm of 59.52. Okay, so now I am going to go to my calculator and see if I can't resolve this. Okay, so first thing I'm going to do is find the log of 59.52. 59.52. Okay, and I'm going to take the logarithm of that, and that's the logarithm of that number. Now I'm going to divide by 0.6, so I have just log v is equal to this new number. Okay, divided by 0.6 equals this new number. So log v is equal to 2.95. So now I have to find the counter log. I have to find the value of v. So that turns out to be 10 to this log, to this number, to the 10 to the 2.95. Okay, I think I have on my desktop some general rules for logarithms that I can post on Blackboard. So if this is going, we're going to go take this to the 10th power. Excuse me, we're going to take 10 to this power, which is the anti-log. Okay, you can think of it as saying to yourself that if the logarithm, if it was the logarithm of 10 to the x power, then that would be equal to x. Okay, so at any rate, 9. So it turns out to be v is equal to 907, and the units that we were working were in feet per minute. So let's see what they ask for here. What's the air velocity in feet per minute? So we have our answer, which is 907. Okay, so I'll clear this out. And I'll clear out my calculator.
This conference will now be recorded.
Okay, so assignment number 3, question number 9. What is the time-weighted metabolic rate in BTUs for the following work activities? And each one of them is given in BTUs, and the duration of the activity is given as well. So similar to a problem we just worked on before, we are going to calculate the time-weighted average. So total work time was 3 hours, 1.5 hours, 0.5, that would be, up to that point would be 5 hours, 6 hours, 7, 8-hour workday. So we're going to average these. We're going to take the time-weighted average over an 8-hour workday. So let's calculate that out. So it's going to be 400 times 3 plus 1100 times 1.5 plus 1500 times 0.5 plus 1800 times 1 plus 500 times 2, and all of that is over a total number of hours, 3, 1.5, 5, 0.5, 1, and 2, which is 8 hours total. So let's take our calculator out and see where we wind up with. Clear, and let's see, 400 times 3, and I'm going to put that into memory. 1100 for 1.5 hours. Add that to memory. And 1500 times 0.5, a half an hour. Add that to memory. And let me stand this up a little. 1800 4 times 1. Add that to memory. And finally 500 for a duration of 2 hours. Okay, and add that to memory. Clear this. I'll record memory, and I'm going to divide by 8. Oops, it was 6,400 divided by 8. Right, let me just recreate this. Divided by 8 comes out to 800 BTUs per hour is the time-weighted average metabolic rate. Okay, so we'll move on to the next question.